much for the introduction. Thanks to everybody for being here. Thanks to the ISFOG organizers for putting on ISFOG 2025 and for the invitation to give this keynote. It's been a great journey and given us fantastic opportunity for lots of discussions, so thanks, Avi. And I'd like to also acknowledge Conleth, Phil, and Fraser, who've co-authored this keynote. But it goes much further than this. So the paper obviously references a lot of relevant work in the area, but I would think that most people here in the room, in the next room, who have anything to do with suction buckets, chances are we've spoken, we've done something together, and you have influenced this keynote in some way, so thank you. I kind of thought, how did the ISFOG start? Where have we come from? So the first ISFOG actually had a keynote on suction caissons for offshore wind. And by that time, there was quite a lot of research done on suction buckets, inclusive of field tests and installation prediction methods for sand and clay. There was a nearshore trial already there, but there was no offshore wind turbine installed in the field supported by suction buckets for offshore wind. Of course, the concept is the same as in what we now call the traditional offshore energy sector. So the suction installation is the same, but differences come from the fact that you have many turbines on a site, which may cover several hundred square kilometers. So you have probably more variability in ground conditions potentially as well. And the other thing is that offshore wind turbines are relatively light. So there's a low vertical load, but high overturning. So we're looking at the schematic on the right, which kind of shows you the push-pull that we talk about. There's an element of fixity between the jacket and the suction bucket to bear in mind as well. And a lot of talk has been about the tensile capacity, certainly in more coarse-grained soil, and that relates to the footprint, of course, as well. So let's step through the timeline. 2010 sort of came and went, and then in 2015, the first suction bucket jacket supported offshore wind turbine was installed at Borkum Riffgrund 1, so the first one in a commercial offshore wind farm. But it was only one, and then we had the next ISFOG in 2015, which outlined the next steps. This is Thoringer who put that together. And the focus was on drainage, the mobilization of tensile capacity in sand, and along the same vein also the cyclic capacity. In 2019, through a Carbon Trust initiative, the state of industry was captured in this document, and there were pointers towards questions around limits of successful installation, so going to layered soils where perhaps the suction isn't transferred past the less permeable layer into coarser material, and again, drainage and uplift capacity. So in 2015, we had a suction bucket jacket on the ISFOG front cover, and the questions that we're sort of looking at in this keynote are, what do we know then? What do we know now? Hopefully a bit more. And what's next? And something that really was of interest to me is how are research and practice linked together? Hopefully they are. So we'll come back to that at the end. Don't worry, this is a paper content. I won't go through everything blow by blow in this talk. So I'll synthesize points 2 to 4. I'll skip 5, and then we'll sort of go more into layered soils, installation, and cyclic response. So, but just a quick recap on where we were in sand. We knew that suction bucket installation was both feasible and predictable, and hence there was also confidence in the expected required suction, so you can size your pumps. And and go all the way through the design and installation process. And that is really exemplified then also in the BIENEN 2, where 20 suction bucket jackets were installed into dense and very dense sand, and I'll come back to that a little bit later. The field measurements there also show that there might have been minor loosening of the soil inside the bucket during installation, but that really is not having an effect on the in-service performance. So that goes hand in hand with the research that has been available. This image on the right-hand side shows a picture from some of the PIV testing that we did initially in sand, which was pretty much simultaneously done at KAIST as well, luckily with very similar outcomes. And we also concluded that you don't want to install the bucket too slowly. Similarly, the mechanisms have been very well known, and also noted that drainage is really critical to what happens. So none of that is new. This is also not new, but I'll come back to this. So I wanted to set up what we're talking about. So the overturning is largely resisted by vertical push-pull. And then if you're looking at tensile loading arising on the windward bucket, from that, you have the options to expand your suction bucket footprint. So you have a lower magnitude push-pull, or you keep your windward vertical load entirely in compression. You can also increase your tensile capacity just by making the skirts longer. But of course, you also want shorter skirts so that you don't unnecessarily increase your installation risk. And for structural integrity, you can increase the wall thickness, but again, that requires higher suction then and may put you in territory that you don't want to be in. So there isn't really, any way to design conservatively if you want both long and short. So you have to get it right. I'd like to come back to this fantastic schematic that was presented by in papers before that Hanning Low published. So as you go along the x-axis and look at your loading frequency, let's just look at the tensile side of things, you progress from your drain capacity at point A to then mobilizing undrained capacity, and you have to look for any limitation by cavitation depending on your water depth. As you move to the right in that diagram, you kind of go more into territory that's displacement limited, and so that's sort of the space that we're exploring with a cyclic loading into tension. So we know that resistance can be mobilized well beyond the drained frictional limit. When we cycle, the excess pore pressure largely cycles with the applied loading without accumulating very much. The vertical stiffness increases with the mean load, as you expect. And the displacement, of course, that you get is highly dependent on the effective soil permeability. So, if we're talking about the drainage again. So this is all supported by various research findings, and the paper, again, has all the literature that points to that. And now we can see that those same points are supported by the data that is monitored in the field. So the diagram there shows field data from BIENEN 1, and then Michael, at the end of the session, will talk about BIENEN 2. So that, I think, is a nice thing that is coming together, but of course, not all questions have been answered because we keep wanting to push the envelope. And we know that in some conditions, average tension can be sustained without there being overly much upward movement of the suction bucket. And what that means, I guess, as we look at ever-increasing turbine sizes, the system becomes larger, the load's higher, the lever arms larger. You go into territories where there's prolonged or sustained tension on the windward bucket. We have to look at how we treat this so that we don't get ourselves in a pickle there. So we're still talking about what's the allowable tension, and along with that, what's the drainage regime and the effects of cycling into tension. So research, of course, has a role to play into that, but we are also seeing here at ISFOG that people are looking at the design approach side of things, so looking at probabilistic views of considering tension, sustained tension. Okay. Let's now look at installation in more complex soils. So this is a video from centrifuge testing of a half bucket into a clay over sand with a self-weight penetration. Then we're closing the valve, we're installing by suction, and you can see that the clay layer does come up and there's a gap forming. But you can also see, I'll play that again, that the suction is being transferred into the underlying sand layer. And what we really chose to do in this particular test is to select onerous conditions. So we really had a very thin clay layer at the top there, and I'm trying to stop it there for the minute. And very dense sand underneath. So what we're looking for really was just that drainage barrier to see whether we can or cannot transfer the applied suction through that thin clay layer, what happens to the sand underneath. And of course, if you're in dense sand, you get your highest chance of highest resistance and things not working very well. Another point I would like to make on this is, yes, there is uplift of the clay plug and a gap forming in this example, but it did not mean that the installation stopped. So we were able to install the bucket in this example and other conditions to full depth, and that worked fine. But of course, if you've apply the suction to lift the plug or to create some suction transferal from underneath the bucket lid to the underlying sand layer during installation, then the question is what happens during cyclic loading when you have a similar situation happening, and you get a clue of that from this extraction, which is also sped up 10 times, so it's not quite as dramatic as it looks on the video here. So that's the end of the suction installation, and then you can see that there's again separation between the two and how the failure mechanism is mobilized. This work was led by Raffaele Ragni, who is sitting somewhere there in the back, and as I put this into the presentation, I thought there's really only two people that come to mind who have done suction bucket installation in the centrifuge and in the field. That's Rasmus and Raffaele, so you're 2 in 8 billion. We have looked in this series of PIV tests at a number of different conditions. So this is just a still image, and the general setup was the same clay, same layer thickness, same underlying sand as well, but we applied much slower pumping flow rates, and what that really meant was that there was a lot more seepage happening and a lot more, I guess, time for the plug integrity to deteriorate, and it really wasn't very beneficial at all, so we could show that as well. So you want to look at your plug lift potential. We saw that compared to just installing a suction bucket in sand, within the sand layer in the suction bucket, the volume change is somewhat diminished in the layout case, but you still want to have a decently quick installation so that you just don't pull too much fluid through. And a point that I will make over the next few slides is that the state of the soil plug will have an effect on your cyclic performance. So that was the first foray into suction bucket installation into layered soils. And as I said, it was just a thin layer just to create that drainage barrier there. And in a later campaign with Mark Stapelfeld and Jürgen Grabe from TU Hamburg-Harburg, we then looked at a higher strength clay, but essentially found the same. As you see on the PIV processed images to the left, as the suction installation progresses, a gap starts opening up, the suction is transferred. So in the sand layer, you have a similar response overall, which is shown in the plot on the right, but less volume change. So I should say, to the plot on the right-hand side, you have two curves, the orange and purple, who go off to the side. What I've plotted there is the self-weight stress plus the applied suction over the normalized penetration depth. And those two curves correspond to suction buckets with much thicker skirts. So one was a PIV installation, and you can see that the skirt thickness was 2 mils, as you see in the pictures on the left. The other one was a full bucket, but the same skirt thickness. Not a problem in installation, and in fact we managed to install all of them through the layered soils. But of course, in absolute terms, you require more suction to get there. So really what we're looking at is the bunch of curves. Do I have a laser pointer here in any way? A bunch of curves there. So in the layered soil, it comes down like that, and you want to compare that to the green curve in the uniform sand, and certainly in the sand layer, they line up very nicely. Sometimes you consider not to install your suction bucket in one monotonic sack, so to speak, but for one reason or another, you are looking at alternative strategies to install the suction bucket. So you might be looking at pressure cycling, which has gathered a lot of attention at ISFOG and a little bit here, not at ISFOG, at OSIG, and a little bit here as well. So you're periodically switching the pumps around to essentially pump the bucket up some distance before you then proceed with overall penetration. And you can see that in the plot on the right-hand side, where again you have the applied stress plus suction going through the sand and the clay layer, and then in the underlying sand we cycled, and most of the cycles that we applied really lifted the buckets up. We have found that the pressure cycling is most effective at depth where the frictional resistance is higher as a proportion, and that goes along with what others have reported as well in clay layers, where you have the opportunity to degrade the resistance. And an additional point that we've added was if you can limit the applied pressure to below what it would take to uplift the plug fully, that seems to make a difference. We're finding overall that our results from centrifuge testing agree with field experience, so I'll show you something in the next slide as well. And Patrick Götz will speak about what that means for foundation performance. So I guess we had limited access to field data, but we did what we could, and also looked at how we can predict what resistance you encounter when you cycle the bucket, rather than use a monotonic installation. So that's shown for a clay over sand profile on the right-hand side there, where the red line is the field measurement, and the black dashed dotted line is what we've calculated with a CPT-based approach. And if you're interested in that, you should find all the relevant information with pointers in the paper as well. Stepping forward now to the cyclic response in layered soil. Just to show here the installation profile so that we know what we're looking at. Again, a clay over sand configuration. And please stay with me for this one. I will talk you through the plot, and it's not as scary as it looks. So in the end, I want to draw your eye to the green line, and we'll perhaps first look only at the plot on the left. So this is a clay over sand example where there was zero mean stress applied. And as you see, there were packets of 1,000 cycles each, regular cycles, and every 1,000 cycles we increase the magnitude of those cycles. So the green curve gives you the displacement of the suction bucket, where intuitively up is up and down is down. You see two dotted lines in the graph as well, there, that give you the plug uplift resistance and also the frictional skirt resistance, which are relatively close together. But if you look at it purely sort of from a drained frictional conservative design approach point of view, this is all that the suction bucket should be able to take. And then the applied load is shown in the envelope with the black curve. What the skirt has taken out of that applied load is in red, and the pore pressure is in blue, so that you can relate. And in a nutshell, what we can see is that and our intent, I should say as well, was really to cycle the bucket until it came up. So we wanted to make it pull out of the soil. That was the intent behind the test. So as the loading increased, and you can see certainly at 4,000 or 5,000 cycles, we had reached the threshold. The suction bucket should have started moving. It didn't. In fact, it settled a little bit. And you can also see where the excess pore pressure sort of migrates. And it took until cycle about 9,000 for anything major to happen, and only from then on did the suction bucket pull out. So it could withstand cycling well beyond the drained resistance. To contrast that, the image on the right-hand side shows pretty much the same, only that we applied a slight compressive mean stress. So intuitively, you would think that should stay in place better or maybe settle a little bit. But actually, the bucket started coming out of the soil at about cycle 7,000. And we had a lot of discussion around that, but in the end concluded it had to do with plug integrity, so with the history of the installation itself. This is a similar plot, just different loading packets applied and different soil conditions. So here we're looking at a sand layer that overlies a thinner clay layer and sand underneath. The lines mean all the same things in the plot that is shown, and you can see that the loading is sort of more storm loading type. It ramps up, it peaks, it calms down, then there is a period of calm, and then we go again. But each packet we've applied with a larger amplitude. So we are going well beyond the drained frictional resistance and also the calculated plug uplift. but the bucket is very happy to be where it is. In fact, temporarily it settled a little bit, and what the little clay layer does inside the bucket is that it confines the upper sand layer, of course, so that that responds undrained, and that gives it the high resilience to tensile loading. So going back to what that all means for offshore wind turbines in the field, yes, we are still talking about allowable tension, and we're still talking about the drainage regime, how we can cycle into tension. And in the layered soils, we have the additional thought about plug integrity that you want to look out for. So we've seen data, certainly from research. There is experience now offshore, also in more complex soil conditions in the offshore wind regime, and we're hearing more and more of that, which is great. But I think a little bit more is required to put it all together and have us confidently apply the findings in design. And I do think that numerical modeling has a role to play here as well. I've spoken a lot about physical modeling, centrifuge modeling, but there are things that we can't see or measure fully in those physical tests. So I think there are additional insights that we can get. And we can also cover a broader parameter space and perhaps also more cycles than we can otherwise. I'm surprising myself that I haven't gone down some tangent and have plenty of time up my sleeve. What I've presented today really relied on the large body of research, which of course for general applicability looks to readily available and well-characterized soils. So we're looking at the silica sand that you buy from a quarry in bags, kaolin clay, again, that you mix up in the lab, and that's great for our understanding, but really we need to look at a lot more broader soil conditions, natural soils that we find at offshore wind sites. We do know that drainage is important, and for example, how your suction bucket responds to tension, of course, also depends very much on what the tip resistance does. So if you mobilize excess pore pressures there and you generate more of a tendency for settlement rather than ratcheting yourself up because you're essentially bouncing off quite a rigid bottom, then that shifts things around quite a bit. So I kind of put on the slide sands, clays, okay, fine, silts, we don't really quite know, and that would be certainly worthwhile understanding for prolonged tension as well. Again, if we're looking at the binary sand clay, what comes to mind is if anybody ever thinks of suction buckets in a context of glauconites that presents as sands and then transform completely when sheared. Not sure what the confidence level is if we were asked to do a design today. Closer to home, and Ulysse, I stole a photo from you, hope that's okay. We're looking at variably cemented carbonates, and we have known for a long time that they behave very differently to silica sand, and but we don't have a clear delineation, I guess, where the absolute limits are to installation and how they would perform then in service as well. I have lots and lots of conversations around offshore wind turbine foundations under cyclic loading. I think we are some way away from being confident that we can reliably predict what happens in 30 years. So that is certainly very much an area that needs looking at, and perhaps it hasn't always been design driving so far, but that can certainly change, let's put it that way. Where I see a lot of value is, and what I've hoped to tie into this keynote is the value of field experience, checking that against what we thought we'd learned from research, hopefully it ties together, but also seeing where we are with our prediction method, how that lines up, and what else we need to pay attention to. So I guess to sort of pull together what I've spoken about, the installation as such as possible, predictable, including in layered conditions, the in-service performance, I think, on the whole, is better than a lot of people thought possible for a while, although the drainage role was flagged very, very early on. That's not something new. But certainly the attention to the plug integrity in layered soil is something that came out very strongly from the research that we have now accumulated. I think the key takeaway, though, overall is that research and practice have linked well. We haven't gone off on a tangent and we see something completely different in the field and we've diverged. But certainly there's more things that we can make use of so that going forward we can do things even better and in new areas where we're looking at. I would like once again to thank you also for not falling asleep after lunch. And I have one last thing that I would like to speak to, a request to you really. So Anna Pache and I have been asked to contribute a state-of-the-art lecture on offshore geotechnics at the ICSMGE conference next year in Vienna. And if you could scan the QR code that's shown here, you can also find it by the registration desk at the NGI and the COFS stands. It would be great to have your views, your inputs. It should be a few minutes quick click-through survey that you can do on your phone. It's anonymous. We do ask for some general demographics at the end, but the survey itself is anonymous, and it would be fantastic if we had a lot of responses to rely on to inform parts of the keynote. Hope I haven't forgotten anything there. Thanks very much.